Yeah, so this was from a talk that Witten gave around 3, 4 months back at Berkeley, and then he also put up this article November 12th. This has to deal with the Euclidean path integral in GR. So we don't know if this approach still works, but what we essentially do is we integrate over the metric in GR when you're taking the path integral. And Euclidean because of the change in signature, Wick rotation. So when you're dealing with these complexified versions of the metric, right? So like it can lead to some nonsensical solutions, like a universe that started out from nothing and all this stuff, which actually does not give us much information. So Kontsevich and Segal, these people came up with a criterion which actually allows you to define sensible path integrals or quantum field theories on complex backgrounds. And we'll go into what that criterion was. And this seemed to reliably separate allowable and non-allowable metrics. They did it in the context of axiomatic quantum field theory. They had, it was not much to do with quantum gravity, but Witten used some examples, which we'll go through to specify this. We know about how Hartle and Hawking worked on the Kerr black hole, and even after the metric was complexified, they were able to get the same thermodynamic solutions. Another important thing to note here is what saddle points are. So do we know what saddle points are when you're looking at the action on the path integral? Go ahead, Pradyut. Yeah.
So, like I was just reading this up here, and it's just like when the angular, so in the Kerr metric, the angular, given that the angular metric is real, you have
Part
a real this thing. But then when it is complex, like you have imaginary time. So I mean, like, what does like? I mean, isn't that like just some sort of like what physical implication does that have? Because
well, we'll actually look at what physical implications it has in this paper in terms of quantum gravity. But this is the Wick rotation trick that's happening here, essentially. But yeah, we'll look at what's happening. So you have these saddle point solutions, which are basically when you solve for the equations of motion within the theory that you're trying to build, you get these saddle point solutions, right?
Saddle points are like these points where like your solutions start looking different from each other, right?
No. They are when like, so saddle point is like when you set the derivative equal to 0, first derivative is 0, but it's not a maxima or a minima.
Yeah.
Like for the curve, for like f
well,
of x
not the
equals
absolute maxima or minima. Yeah.
Exactly.
They essentially solve your equations of motion.
Okay.
These points. These are the points. Anyway, so let's keep going.
Well, like in general points, but in our case, it would be like field configurations.
Exactly. Which are itself points in the field space. Okay. So let's see. And also he tries to find connect this criterion to finding an integration cycle in the complex plane, since we have complexified the metric.
what is an integration cycle?
Basically the contour along which you can integrate the path integral, because you can basically take different contours, right, in the complex plane, over which you can integrate the path integral.
Why do we, okay, so we are talking about a Wick rotated like path integral right now, or do like or do like ordinary like real valued like path integrals have in context of gravity, right? So in context of GR, do like what is the I didn't get the term like complex saddle points exactly, because like why do you need to complexify things? Like why do you need complex saddle points when you can like still have like real saddle points? Like
no, we are trying to see if there is any physical meaning behind.
As a follow-up to what Pradyut asked, like, can you give like a little bit of motivation behind considering a complex metric in this case for gravity?
Okay, so what we are essentially trying to do here is somehow observe all these spacetimes which have complex time, right? When your Minkowski metric and Lorentzian metrics, all these things. So whenever you're dealing with a theory of quantum gravity, you need to start considering that. Now, what we are trying to do is somehow merge QFT and gravity in some way, and this is one of the ways to do it.
Okay, so you're talking about like integrals in the sense like a general QFT integrals and not strictly like path integrals, right? Okay.
So what do you mean?
Quantum gravity more like, not exactly.
Yeah, it's not your typical path integral. It's a gravitational path integral.
Okay.
I think I have a note which goes into that as well. We can have a look at it maybe after I go through this. So yeah, you need an integration cycle over the complex matrix. Yeah. A satisfactory extension of their proposal beyond perturbation theory. So you perturb around these saddle points to actually gain find exact solutions or near exact solutions, rather approximate solutions. Yeah. So let's see what all this is about by taking the usual flat metric in some d dimensions on the real space. So normally when you're considering things, R is non-negative and d omega square is basically your spherical metric. Okay, one way to generalize, so there are multiple ways to do this as well. You can complexify the real or the angular parts. So let's say to generalize this, we complexify or relax the condition for R to be real. We can make it complex. So R runs over the complex R plane as well. So you have this parametered function basically here, where U is still non-zero. Yeah. Yeah, in that case, it's flat, all of that. R of U remains complex valued. Now, if you want a complex manifold without a boundary, now we are trying to simulate the universe. We should take U to run over a compact interval. Yeah, go ahead. Feel free to stop.
So when you, when you were like, so when you relax the condition for R to be real, it's basically like like non-physical. You have some sort of non-physical dimension coming, right?
Yeah. That's the complex part of things.
Okay, so in the sense, like it is not exactly an observable, but it involves some sort of like a gauge freedom or some sort of like.
I don't know if I would call it a gauge freedom. You'll see its effects on the evolution of the universe, though.
Okay. Okay.
Yeah. Yeah, we get more options if we complexify the angular part as well. Okay, so we want to know if this is an actual allowable metric now. Like, we've done all this complexification. Like, does it actually make sense to define a QFT on this?
So,
Right.
are we just talking about the algebra? Like in the sense,
Actually, yeah,
algebra.
it is an algebraic condition that we'll come across that will let us know if it's allowable.
Okay.
So let's see. Okay, if we complexify, blah, 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 we have the same thing, and yeah, this is not that important. Okay, puts a strong on. So there are some immersions coming here, all of that stuff, which is not really important for us at the moment. Let's see. Okay, yeah. I'm trying to see where he actually talks to you about. Okay, I think this is the part. Varying complex metrics. So yeah, you'll have to probably cut out some of these parts. It's fine since we're going through a paper. Yeah, so what he's saying is the non-complex metric, the universe that it defines is essentially an embedding within the complex space that we have just now defined. So the two complex metrics, different immersions, blah, blah, blah. Okay, this is not that important. Yeah, so that is one way of defining it. So to get the exotic complex matrix RD, we can simply use the same construction, but now with U ranging over the semi-infinite interval, we have the same things. So largely you get what is happening here, right? Yeah, if you have any questions, feel free to stop me. Yeah.
I wouldn't say I definitely wouldn't say I understand what's going on, but it certainly seems a lot better motivated right now than like before. Like before, like if you just like came and told me that complexified metrics, I'd be like, why?
Yeah.
But at least now, like it makes sense because there's so much more richer mathematical structures for you to explore.
Exactly. Yeah. So
and also like could you go, so you said that what was his name? Kontsevich and someone else, I think, that they had imposed, or rather they had found out certain conditions.
Yeah.
And you said that what that does is that kind of tells you which metrics can correspond to real physical theories and which are just quote unquote nonsensical. And you also said that they're derived from axiomatic QFT.
Yeah. So
okay, could you just go over that?
Yeah, I can actually go over the result. So this is basically it. Just a second. Quantized fluxes. Yeah, this is the condition. So what did I do? Never mind. Yeah. So what this is essentially when you have a complex metric. Actually, let's go through another paper. Is this the one? No. Just a second. This paper was a follow-up paper to that, which actually talks about it slightly better. Which, if I can find, would be nice. Actually, you know what? I'll show you. Yeah.
So when we were like so when we were talking about like wormholes and like complex dimensions and all that, right? So see, wormholes in the sense it is wormholes that are not really connecting. So this is the confusing part for me, right? Like because if there is complex.
Hello. Can you hear
One
me?
is like, are you allowing it to be like purely complex, or are you allowing it to be both like real and complex? So
It-
with
when you
both
say
things are
Think
like
of
complex,
it, wait,
completely
wait. Think of it like an analytic continuation, if anything.
yeah, it is exactly an analytic continuation, by the way.
so it is both like it's just like primarily real, but like whenever you need to like create some sort of an analytic continuity, you just bring in like
No. That's not what we're doing. Just forget that. Just what we're doing is we're consistently saying that instead of reals, we can now put in complex entries. That's all. It could be purely imaginary, it could be purely real, or it could also be a complex number. All of them are perfectly fairly allowed. See, so like if you're going to analytically continue some function, it's going to hold like it's done in a way such that it holds true over the complex plane, barring poles if it exists. But that's an entirely different discussion.
So like what I get from that is like we can basically put it into like 2 or 3 different kind of categories, like based on whether it is what you're allowing is real, complex, or like a mix of both. So when it is a mix of both, like you do have the more.
What do you complex implies that there is a real and imaginary part.
Yeah.
Yeah, okay.
So
So
the real part is just
imaginary, real, like purely imaginary, purely real, and like there is also complex, right? So when you talk about like just generally complex like dimension, that is enables like the possibility of wormhole. But like if you talk about purely like imaginary dimension, that would basically behave in every practical sense that a real dimension, real this thing would. But in the sense like there, I'm just trying to like put it into different categories and basis of
I don't
solution.
think I don't necessarily think that works because even work purely like you that would be kind of like real. And I can see why you'd think that, but like I don't know. I somehow feel like just the fact that you are purely imaginary gives a lot more structure than reals. Because we want things to be analytic.
I mean, you do
Automatically,
have
a
like
lot
if you
more
don't have,
conditions imposed right off
yeah,
the bat.
if you do have like some structure with like where it is complexified with respect to another like dimension or another degree of freedom, what you're saying would make sense. But if like as the dimension itself, like you're treating it purely imaginary and it doesn't like really yeah, it doesn't really mess with the other. But I don't think that would be possible. Yeah, because
I,
like when you're doing a path integrals or when you're integrating, you just like integrate over space time. You don't deal with like individual dimensions. So yeah, okay.
yeah,
Anyways,
I still don't quite understand it, but we can circle back to this. What you're talking about. But since we were on the topic of how to define these allowable metrics, so what is essentially happening is, yeah, there's a p-form gauge field essentially,
Mhm.
and a p+1 form field strength. And this is the action over there. So what actually means for a metric to be allowable is essentially this action integral has a positive real part for every non-zero Q form F. Okay. With this is when there's a space-time of dimension D and the Q form is less than D, obviously. So this amounts to this condition that you see here. Yeah. Which is
Should be
pretty
greater
clear.
than zero. Okay,
Yes,
if it has to have a positive real part, then yes. Okay, it has to be greater than zero at every point.
exactly.
Okay.
And the motivation for imposing this positivity is the path integral of P form to be convergent, gauge field to be convergent. That's what we're essentially trying to do. Yeah.
Okay. Fair.
Okay. So, okay. Yeah, this is where he talks about how I think this has I don't know if it's exactly related to this, but I have a feeling this has to relate to the Ostwald or Schrader axioms of quantum field theory. we can have a look at that sometime.
Sure.
Yeah, is imposed for okay. Yeah. That's basically it.
That's fair.
Yeah.
That's really cool.
And this is the next part. So for the case that q equals 1, we can see how this works out, right? This tells us that the real part of this matrix, which is sort of like your Jacobian, is positive definite. So you can write it in this form since it is complex. A and B are simultaneously diagonalizable. So now what you do is you pick a basis of the form of delta ij. It's orthogonal, and this can also diagonalize B because they're simultaneously diagonalizable. And therefore, we have this, the inverse. Yeah. And then this is the key part of it. So the metric can, I don't know what's happening. Anyway, the metric can be written in this form since it is diagonalized, right? Where your lambda I are your eigenvalues, essentially. Yeah. Now what you do is, so for this to be positive definite, this has to be true.
Does your like whole simultaneous diagonalizable like that condition, does that have anything to do with like the phase space? Because like what I'm like what's coming to mind is like when I try to visualize A plus IB, and when I try to see the metric like correlated to that, I mean the determinant of the metric correlated to that, then I'm trying to say like, so basically you're just like, you have some sort of like vector around a circle, which that like, and that space, right? So a unit circle or like,
if you're trying to visualize eigenvalues on its own, yeah, I think you can do that, but it has nothing to do with the phase space. If I'm well, you can draw connections to the phase space, but it's not necessary, I think.
Okay.
Yeah. Okay. Right. So yeah, it basically equates to this condition over here, which holds precisely if this is true. And this is the crux of the argument. So we have a simple criterion for metrics to be allowable. So the other paper that I was talking to you about is this, which actually goes ahead and looks at.
Rahul, sorry to bother, but like, could you like fit it to the screen? Because I'm on my phone and it's kind of hard to read. Yeah, thanks.
Yeah. So here he looks at. So this is Jean-Luc Lenners from Max Planck. Here he looks at 3 different metrics. The ADS metric, the generalized Robertson-Walker metric, and the no boundary solution of Hawking. And what he begins to find is when you look at the space of complex metrics, so the red regions are the ones that are not allowed. So this is where your integration contours, all of those come in. And your blue dots here are your saddle points, right? So around these saddle points, you have both allowable and non-allowable metrics. But how you actually classify allowable and non-allowable is the KS criterion. So you calculate it for all these types of metrics. And I think this is for the no boundary proposal. The white, the white region is what's allowed. And your these are your essential Lefschetz symbols, which are also the contours of steepest descent. Basically, like your gradient. If to call on some intuition, it's not exactly that. Yeah, within these spaces, and your saddle points lie along these thimbles.
Like, wait, 1 second, can go up.
Yeah.
What is what is the plot basically?
Okay, so what you're trying to do here is, let's see. Actually, I can start from this. So this is your Robertson-Walker metric generalized. So all your, most of your metrics that make sense have to fit in this form, where n is called some lapse function. Yeah. If you even look at your flat metric, you can see that it sort of fits into the same form with some, with n being defined in a certain way. Yeah. I think my internet is bad, so you guys are cutting off, but regardless, I'll just keep going, I guess.
Yeah, your voice is perfectly clear, so I don't think.
Okay, fine. Yeah. So yeah, this is the, let's see. Okay, this is the gravitational path integral with the cosmological constant of lambda that we're taking, and this is the metric.
Wait, 1 second. Could you go back again? Sorry, cosmological path integral. Is that the
no gravitational path integral with cosmological?
Sorry, gravitational path integral. So the measure in this case is the.
Yes.
Oh, okay. All right.
Yeah.
And,
that's how you have these gravitational path integrals. The measure is always on the metric.
Okay, so few questions here.
Yeah.
So what would the saddle point of this quantum? Would that be the Einstein field equations, or
that will be your solutions to
the field equations?
Actually, let's go through this process. Here we actually find the saddle points. So this is the action of this regime, right? Arrived at after performing some integration by paths. Yeah. Then you have your canonical momentum and the equations of motion and the constraint, all of that. Yeah. So this is what you essentially solve for. With some manipulations, the solution is given by this, right? And then
what you got? Okay, okay.
Yeah.
Got it.
Yeah. Using the solution, the path integral over Q. Okay. This is basically how you can do the path integral, which brings it to this form where n is your essential lapse function that I was talking about. And that gives you this form, right? So this last integral.
Why isn't it quadratic? Shouldn't it assume two saddle points? Question mark. Why are there 4 saddle points?
Because
you're solving for n.
Yeah.
Oh, okay. Yeah. Okay, that's fair.
Yeah.
All right. Okay.
And
I thought you were dealing with like Q0 plus Q1. That's why.
Oh, no. We are essentially observing the lapse function, because that's what actually dictates whether you have a real metric or a complex metric. All those things.
Okay. I see.
Yeah. Right. So you have 4 saddle points here, which essentially solve the above equation.
So wait, the x and the y are like real and complex parts.
Yes. Yeah, you're right. Okay. So that's what we are essentially trying to do. Now, this is what we do for other metrics as well. And based on the case criterion, we see like to the left, like to the north of the saddle point and the n line, the n equals 0 line, like are the metrics allowable or not? And we do all these manipulations. The specifics can be found through the paper. I can send it to you guys. But yeah, that's how you find. I think there's some background. Yeah, never mind. So yeah, you essentially have these solutions.
Okay, so it is so okay, so it's like some sort of like the way you define your lab function, like range with which you can define your lab function is
Yeah.
basically corresponding to sort of like how much time shifts. I mean, now like I don't still clearly understand, so like how fast time moves, and then using that you can like kind of somehow correlate it to like how much you can complexify a particular dimension or something like that. Like, are you
I
trying to
mean,
make
all the things that you've stated, the labs function has all that information.
okay.
So I don't know if that's what you're saying.
No, in the sense like when we're trying to set like limits as to how complex a metric can get. Yeah, I mean like we're actually like talking about a space like which is defined by the lab functions, right?
Yeah,
Like I mean where the lab functions and that particular
yeah,
definition still holds.
yeah,
Okay.
yeah, yeah. That's what we're doing. And here we can see that around, I think this is done around saddle points. We take different contours. Some of these actually violate the condition, the KS criterion. So if we deform it slightly though, we have something that's well contained even at infinity. Yeah, so that's how you try, you see. So you can say that, okay, you can deform anything, right? You can deform any contour to fit this condition. But you can't actually, because let's say you have a value that is, so yeah, you have this for the initial, right? If anything, if sigma is above this, it's already violated no much how much you can deform it. And your remember sigma is your the sum that has to be less than 5 that we spoke about, the essential case criterion right here. Right here. This is essentially your sigma, but yeah. So this actually allows us to differentiate between allowable and non-allowable metrics. But yeah, this is a bit all over the place, but via the nature of the call, it was, yeah, bound to be like that. But yeah, that's essentially what this paper talks about in different cases. We can also have a look at the gravitational path integral, what it is talking about. There we go. Yeah, actually, I haven't even read through all of this paper, but should be fairly straightforward from this. Actually, I can send this to you guys.
Yeah, that would be great.
Yeah.
Because I just haven't had much time like getting a chance to like formally explore relativity. I've just had one course, so like really haven't had much time to play around with it. So this was great.
Yeah. Okay. Yeah. Do you guys want to share something else?
We could go back to addressing Pradyot's question about gauges.
Okay.
Because I think there's a decent amount of physics to be spoken about there.
Okay. Yeah.
Yeah.
So the question was essentially like, yeah, so to a certain extent, I understand like what gauge invariance means, like when you define your like gauge to be like shifted by derivative of the potential, right? In relation to invariant. picture from the thing.
We are gauging or and why
The
like what does it mean
shift
to
by the
have gauge in
derivative, the plus d mu a mu,
Okay.
that
Alright.
part, right?
Okay,
So
let's forget that in a quantum context. Okay, let's go back to classical, just
Okay.
Maxwell's equations. Okay, so what we see in Maxwell's equations is that if we basically take our four, right, our four, what it's called, I'm not sure. Anyway, you take
Yeah.
a mu, you shift it by a total derivative. What happens then is that your Maxwell equations remain unchanged.
And
So what
this
that
is
effectively tells,
also, yeah, this also, like, you don't even need to actually go to, well, Maxwell's equations, because this is the property of that you see in vector calculus, right?
Yep.
If you take the curl of the gradient, it is zero. If
Yes.
the curl of gradient itself, yeah. So if you add, so how is your magnetic field defined? B, it's the curl of your vector potential.
Exactly.
Yeah,
So if you add in another
Yeah.
gradient, it's going to give you 0. So like basically, yeah, it's the same as like integrating a boundary term and setting it equal to 0. Like you see these, there are many different places. So especially when you have differential equations, there are many different subtle ways of adding in your zeros into the equation. You can add it as like a total derivative term. You can add it as a derivative of a constant and blah, 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 blah. Each of these imply that there is a certain redundancy in your description of the system.
Yeah.
That's all it
So
says.
basically, okay.
Yeah, and
So
why?
basically,
Go ahead.
go ahead. Like,
No, I was going to add on that. Let me see if I can pull it up. Yeah. So we have this equation. Let me share screen again. This was from my E&M class. Yeah. So this is the equation for when you have like varying magnetic fields, all of that, right? This is okay. Let's actually see where you get this equation from. Blah blah blah. You recognize it until this. Wow. This yeah. Okay. Plugging the blah blah blah. Okay, you have this part. So this is where you get this from. Yeah. This is clear to you, right?
Okay.
This is from Ampere's law, basically.
Okay.
Yeah. And then you have this, right? So we have some, we recognize this as, the wave equation, right?
Okay, but okay. So one thing that I'm not able to like clearly pinpoint. Okay, so the thing is, okay, I get how the curl of like the gradient of the wave potential will be like some sort of like invariant magnetic field and all that. But like, how does it exactly show you that the net force or the net potential generated by like this combination of electric and magnetic field, how does that how does choosing what you define as your electric field and what you define as your magnetic field, like you can change that, right? That is basically the principle of gauge theory. So how so you have a net potential. It doesn't matter whether it is electric or whether it is magnetic. You can just shift that kind of a like potential.
Are you asking how F equals dA?
Yeah, no, I'm just asking how like you're like net, like how you're actually like talking about the shift. And this gives me some sort of a condition. I get that, like in the sense like you do have like all these invariant terms coming in, like you have this invariant space coming in and all that. But like I don't really get how you translate it back to this like concept of like E and B, and like how A is independent of like what you define as E and B.
That you can see. Actually, you don't. Okay, fine. Let's simplify the case further. let's only take potential as in scalar potential, right?
Mhm.
Your voltage, yeah.
Yeah.
The zero of your voltage is actually not universally absolute, right? You can shift it
Mhm.
to
Yeah.
whatever you want to, but your
Mm.
electric field still remains the same somehow.
Yeah.
Why does that happen?
Because voltage is measured with respect to your electric field.
No, because your voltage is relative, and how is it defined? E equals gradient of phi. So
Yeah.
gradient of some function should equal 0.
Okay.
That is how you get the function. So even if you add that function to the potential, it will still go to 0.
Okay.
So
Okay.
it leaves the electric field invariant. So you need to find that kind of a function. It's basically just mathematical manipulation.
Okay. Okay.
But
So
yeah,
in this case, it's like saying moving the potential up and down is again fixing the gauge at some point.
yeah, exactly. It's
Yeah.
actually the first time you encounter fixing a gauge. They don't just tell you that. That's it.
Mhm. Mhm.
And why we try to even fix gauge? So if it's a mathematical manipulation, like what's the use? Like, is it telling us anything about the physics of things? Turns out yes and no. No, because why we essentially do this is to simplify our equations. So as I was getting to the point, this is, you recognize this as your wave equation, right? Fairly
Mhm.
straightforward. But there is some ugly thing here, that is a divergence of a divergence, and you have like this divergence and the time derivative. It's kind of messy, right? You want to get rid of that term. Turns out you can by using something called as the Lorentz gauge. This is the Lorentz gauge. Now, if you make this choice, right, this as all this term will go to 0, and this remains.
Okay.
It's your simple wave equation. So Lorentz gauge is usually used for time varying electric and magnetic fields. That's when you have this equation.
Mhm. Mhm.
What we've been using before this is this essentially. The Coulomb gauge, when you solve for I don't know, Poisson equation, when you have an electrostatic field and you're trying to find the potential everywhere and stuff like that. So that is essentially what is happening with gauge transformations. Now you promote this to some P form. You need to sort of define what the curl is there. And that's why your force takes that form of dou mu a nu minus dou nu a mu for F mu nu. So yeah, that's essentially what is happening.
Okay.
I'm just gonna, okay. So that makes sense. That makes completely sense in a classical context, right? But here's the thing. In a quantum context, there is a much better motivation for that. But at least that's my opinion. In the quantum context, how you get to F mu nu, you define it as the commutator of your covariant derivative.
Yeah.
Which naturally gives you the interpretation of F mu nu as a field strength tensor as defining a curvature.
Yeah.
And I think like that's just much better geometrically motivated than like, because I feel like, at least like, especially now that I'm taking a course in quantum field theory, I feel like a lot of the things that we did in like in E&M and classical mechanics, they're just much better motivated here. Because for some reason, like when you do E&M and classical, for some reason, like they don't go into the full mathematical formalism for this, but they kind of do that when you're going into field theory. So this has given me like a much nicer appreciation for all that's going on.
Yeah, no, that's true. Yeah. you can actually see this happening even with your Riemann tensor, all of that. It is also a commutator essentially that
Exactly.
you're calculating,
Yeah.
right? Yeah. So
And if you want to bring in another similarity, like in your space of the surface, like, okay, so every Lie algebra comes with a manifold. The connection on the manifold is defined by your AMU. AMU is your connection, which is basically the same as like what the Christoffel symbol does. And this was actually one of the very big initial motivations to be like, ooh, this must be, because they both have this nice geometric picture, we must be able to unite space-time and all of this. But then anyway, that's an entirely separate discussion. But yeah, there's just a very nice geometric picture that's going on in both cases, and they're very similar. But the only difference being that at least in QFT case for the fields, it's all linear. That's why things are so simple. That's why your connection is just like AMU with one index. But GR is inherently non-linear, which is why your Christoffel symbol gets so wonky.
Oh yeah. By the way, like I was just going through like this notion of connections in GR, and then I found this like interesting article by Sean Carroll. Let me just like see if I can pull that up. It basically talks about how so how the Christoffel symbols, how that actually reduces to if you just start off with some arbitrary definitions for like what your Christoffel symbols would look like, and then when you actually look at it, like when you define it as the differences between the derivatives of the metric and all that, right? So it's actually a it's very interesting like set of like conclusions, and I think we could like go over that in some of the call. Yeah, that's something I'll just want to like mull over it. So yeah.
I think hope that gives you an idea. Although again, if you consider Aharonov, all of that, setting your gauge actually has a quantum mechanical effect, though, which is observable. So even though this allows us a
This
degree
connects
of
to the Berry phase and Berry curvature and all that, right?
Yeah, it does. Yeah,
that's something I want to discuss. That'll be fun.
Yeah.
The AB. I never know how to pronounce that name. Aharonov.
Aharonov.
Yeah, that effect and the berry face. It's beautiful.
Yeah. So yeah. All right. Any others? Anything else?
If I'm not completely mistaken, there is a relationship between how you do the Aharonov-Bohm thing, like the explicit calculation for that, and Wilson loops. I think it's because you're defining your Wilson loop along something that is not topologically trivial. You pick up a number, you pick up a winding number as you go across, and that defines your difference at the end of the day, which is what we see. So yeah.
That is also something that we can go into, Wilson loops and all of that.
I think we touched upon this in one of the podcasts with Vasudev. Like, we need to explore this further.
Yeah.
Wilson loops is such a powerful way of figuring out what your topology is. Because it's always like, because it's defined as just something around a closed loop. If you do it around something that's non-trivial, it's going to give you something funky. And I think that's a very good way of like trying to analyze whether the surface you're working on, whether that has a trivial or non-trivial topology.
Yeah. All right. I think I'll stop the call. Yeah, stop the recording. Yeah.